Assalamualaikum. Hi, my name is Faizatu Maisara binti Muhammad Johari, and I will be presenting the introduction part. So first and foremost is about Newton's second law. So if F is the external force acting on an object of constant mass m that moves with instantaneous velocity v, then F equal to mdv over dt, or F equal to ma, where a equals to dv over dt, where it is representing the acceleration of the object. Moving to the next slide. So if the force F is uniform or constant, then we will obtain the result as the following using the formula F equal to m v2 minus v1 over t, where v2 minus v1 representing the changes in velocity and t is the time taken. So as for the object with mass, which is m, that falls under gravity, the force acts on the object is given by the formula W equals to negative mgk, where k is a unit vector in the vertically upward direction, where this force W is called the weight of the object and has a magnitude W equals to mg. The weight W is negative because the weight W points downward. So from the slide before, from equations 1 and 3, we have for object that falls under its own weight, which is neglect and resistance, which is freely falling object. The differential equation for the motion is by using this formula, which is m dv over dt equals to negative mgk, or dv over dt equals to negative gk, where v is the velocity at time t and k is unit vector points upward. So for freely falling object, so integrating equation 4 using separable first order differential equation, we obtain as shown, and assuming at time t equal to 0, the object initial velocity downward is negative v0k, then from 5 we have negative v naught k equals to 0 plus c, where we got c1 equal to negative v naught k. So from equation 5 and 6, the object velocity at any time t is as shown here, but v equal to dr over dt, where r is the displacement above the earth surface. So dr over dt equals to negative v naught minus gt times by k. So integrating equation yields, by integrating dr equals to integrate negative v naught minus gt times by k dt. So r equal to negative v naught t minus 1 over 2 gt square times by k plus c2. Next, at time t equal to 0, r equal to 0, point where the object starts to fall, and from equation 9, we got c2, where c2 equal to 0. Thus, the displacement r of the object at any time t is by the following formula, which is r equal to negative v naught t minus by 1 over 2 gt square times by k. So equation 7 and 10 are for object that falls under constant acceleration.
Okay, so topic 2, problem statements falling object with air resistance. Freely falling object has only its own weight acting on it during fall. So weight is equal to mass times the gravitational acceleration, or W equal to mg, where g is equal to 9.8 meter per second per second. The object equation for velocity is simple. For free fall without air resistance, v equal to minus v naught. Actually, this is V here is the initial velocity, and G is the acceleration due to free fall or gravitational acceleration. And K is the unit vector, T is the time, K is the unit vector, outward is positive. So that's why we have a falling object, the initial velocity is negative because it's point downward, because A point upward. And acceleration is also negative because acceleration point downward. So V equal to, V is the velocity at any time without any air resistance, is equal to minus V naught minus GT. K. K is the unit vector. The object fall with constant magnitude of acceleration, as mentioned just now, which is G. G equal to 9.8 meter per second per second. In real life, when the object fall in the air, the object exert a force on the air to push it out of the way. The air also exerts an equal and opposite force onto the object. This opposite force is called air resistance. The direction of air resistance is always opposite to the direction of the object velocity. So can you see here the air resistance? This is a force which always oppose motion. Okay, so when free fall or object falling downward toward the Earth's surface, the weight point downward, so the air resistance point upward because it's always oppose the motion. Okay, for small object, okay, the magnitude, for it doesn't matter small object or large object, the magnitude of the air resistance increases with the speed of the object going through the air. Okay, so meaning that the air resistance is proportional with the speed. For small object that fall with low speed, uh, the air resistance F is proportional to the object velocity V. F equal to minus beta V, where beta is the proportionality constant that depends on the size and shape of the object and the property of the air. Here you see negative beta V. Why negative here? Because the air resistance is always opposed motion. If the object fall downward, then V is negative. So minus beta times minus V. So we got beta V. So it is point upward. If the object move upward, okay, then V is positive because it move upward. Then we have air resistance equal to minus beta V. So air resistance will point downward. If the object move upward, the air resistance will point downward. So because V is positive upward, so F equal minus beta V, so air resistance point downward. If the object fall downward, then V, the velocity is minus V. So that's why minus beta times minus V, we got beta V, so it's point upward. And for larger object that fall at high speed, the air resistance, or sometimes we call drag, okay, is proportional to the V square. Okay. So F equal to minus beta V square. Okay, again, if the object fall downward, so V is negative, so F will be positive, point upward. If the object move upward, then okay, so if the object move upward, V will be positive, then beta will be shear force will be negative, drag will be negative, a point downward. So you see that the drag or the resistance always oppose motion. So this is a graph which shows that without air resistance, the acceleration is constant. I mean, the object fall with constant acceleration. Without air resistance, there is no drag. Okay, so it's fall at constant acceleration. It is minus g. But we have air resistance, and we mentioned just now that the air resistance or drag increases with the speed of the object. So the drag increasing as the object fall with sufficient time. So we see that the object velocity increases, so the air resistance also increases. But the weight, which is mg, is constant. So as the because weight remain constant, but the object air resistance increases, so we see that the net force decreases. So this net force decreases, meaning that the acceleration decreases. So as the object fall with sufficient time, the acceleration decreases until we see that at a certain time before it reach the earth, okay, the object acceleration is zero. So at this time, the air resistance is equal to the weight. So acceleration is zero, but not the speed. Okay. The speed at this time is maximum, and we call that terminal velocity. So when a jet fall at sufficient time, okay, after a certain time, the object's uh, velocity will reach terminal velocity. So at terminal velocity, the object fall with constant velocity and zero acceleration.
Next, I'm going to present about problem solving, how to find velocity for falling object with air resistance. For an object of mass, which is m, that falls in air, the magnitude of the object weight is mg, and the air resistance of or drag F is the resisting force that increases with object's instantaneous speed and opposing the motion of the object. The equation of motion for the object is m multiplied by dv over dt equal to negative mgk plus f, which is f is falling object, where k is unit vector pointing upward, which is negative, and f opposes motion. Let's see case 1. For small object falling with low speed, the equation of the air resistance is F equal to negative beta multiplied by V multiplied by K. Then the equation of motion of the small object for equations 13 and 14 is M multiplied by dV over dt, which is equal to negative mgk minus beta vk. We can solve the above differential equation as below. M multiplied by dv over dt equal to negative mgk minus beta vk, which is dv over dt equal to negative gk minus b over m multiplied by vk. Then we solve dv over dt plus beta over m multiplied by vk equal to negative gk. Final, dv over dt plus beta over m multiplied by vk, we can get negative g. Integrating using linear first order DE method, where pt equal to negative beta over m and qt equal to negative g, we obtain ve to the power of t over m equal to integration negative ge to the power beta t over m dt. Then ve to the power of beta t over m equal to negative mg over b multiplied by e to the power of beta t over m plus c. Then we can get velocity equal to negative mg over b over beta, then ce to the power of beta t over m. At time t equal to 0, the initial v equal to velocity initial. Then velocity initial equal to negative mg over beta plus c1. C equal to velocity initial plus mg over beta. Replace c in the equation 16 with c from equation 17. We can get the velocity of the falling object at any time with velocity equal to negative mg over beta plus initial velocity plus mg over beta multiply by e to the power of negative beta t over m. Let's move to the case 2. For large object falling with high speed, the equation of air resistance or drag is F equal to negative beta V to the power of 2 K equal to negative beta V absolute value V K. For equation 19, from equation 19, for object that move upward, the air resistance is negative because the object velocity is positive, where F equal to negative beta multiplied by positive V multiplied by absolute value V multiplied by K equal to negative beta V to the power of 2K. For object that move downward, the air resistance is positive because the object velocity is negative, where F equal to negative beta multiplied by negative V absolute value negative V multiplied by K equal to beta V to the power of 2K. We can solve the previous differential equation as below. M multiplied by dV over dt equal to negative mgk plus beta V to the power of 2K. It is downward motion, which is dV dV over dt equal to negative gk plus beta over m multiplied by v to the power of 2k, and the result is dv over dt equal to negative g plus beta over m multiplied by v to the power of 2. Integrating using separable first order dE, we get integration 1 over negative g plus beta over m multiplied by v to the power of 2 dv equal to integration dt. Then we solve it to negative integration 1 over g minus b over minus beta over m multiplied by v to the power of 2 dv equal to integration dt. We get negative m over beta integration 1 over mg over beta minus v to the power of 2 dv. We get integration dt. Then negative m over beta multiplied by 1 over square root mg over beta tangent hyperbolic inverse multiplied by v over square root mg over beta equal to t plus c. Square root m over beta g tangent hyperbolic inverse multiply v over square root mg over beta, we get t plus c. At time equal to 0, the initial v equal to velocity initial. Then the equation of motion of the object for velocity at any time is v equal to negative square root mg over b tangent hyperbolic multiplied by t over square root m over beta g minus tangent hyperbolic inverse velocity initial over square root mg over beta for falling object with air resistance or drag.
Finally, conclusion. For a falling object with no air resistance, a freely falling object will fall with a velocity v equals to v minus gt with a constant k. On the other hand, for a falling object with air resistance, the object will fall with a velocity as the following. For small object with low speed, or as the following. For large object with high speed, both objects, when fall, their acceleration will decrease. For example, for a small object falling with air resistance, the equation is as follows: m in respect to dv gk minus beta. For a falling object, the velocity is minus v. With sufficient time, the object falls. And then it is 0 equals to mg minus beta minus times by minus b, because air resistance increase with speed. Then the speed v is equal to mg divided by beta. At this speed, it is normally referred to as a terminal velocity. At terminal velocity, the falling object acceleration is 0, whereby there is no more increase speed. That is all. Thank you.